You see a fuzzy dot on a screen in Chile. July 1st, 2025. The Atlas telescope catches something moving through the Milky Way's star field. Not just moving, blazing. At 137,000 miles per hour, this object tears through space on a trajectory that says one thing. It came from somewhere else. Not Mars, not Jupiter, not even the Kuiper Belt past Neptune. Another star system, another world. The third confirmed visitor from interstellar space just entered our cosmic neighborhood, and within hours, astronomers know something is different about this one. Bigger than the others, faster than the others, and arriving with enough advance notice that we can actually watch it approach the sun. Its name, 3I Atlas. The numbers say this comet nucleus could span anywhere from 440 meters to 5.6 kilometers across. That upper estimate puts it at Manhattan's length. The chemistry says it formed in a system colder than ours, rich in carbon dioxide, possibly billions of years older than our sun. And the orbit says it will never return. This is a one-time pass through our solar system, and on October 29, 2025, it reaches perihelion at 203 million kilometers from the sun, hidden behind our star from Earth's view for 8 critical days. What happens during that window? What can we learn before it vanishes forever? And why did a United Nations-endorsed planetary defense network just activate a global campaign to track this object with mandatory training protocols? It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the Minor Planet Center's Electronic Circular MPEC 2025, U-142, published October 21st, 2025, NASA's official 3, Where's Our Atlas page, updated through October 2025, and the International Asteroid Warning Network's campaign documentation at iallen.net, all cross-referenced with peer-reviewed observations from the Hubble Space Telescope, James Webb Space Telescope, and the European Space Agency's Mars orbiters. These aren't blog posts. These are the primary data sources from the institutions doing the actual tracking. Now back to the information. That's the Asteroid Terrestrial Impact Last Alert System, 4 telescopes scanning the entire sky every 24 hours, hunting for rocks that could threaten Earth. The network caught something at apparent magnitude 21.5, barely visible even to professional instruments, sitting 420 million miles from the sun. First designation, A11PL3Z. Within 24 hours, follow-up observations from the Lowell Discovery Telescope in Arizona, the Canada-France-Hawaii Telescope on Mauna Kea, and the Deep Random Survey in Chile all confirmed a fuzzy coma around the nucleus. Not an asteroid, a comet. By July 2nd, the Minor Planet Center assigned it the interstellar designation 3Y and the comet designation C/2025 N1, the third interstellar object ever confirmed. The first two, 1I/Oumuamua, discovered in 2017, and 2I/Borisov, discovered in 2019. But 3. I-Atlas arrived different. Oumuamua was spotted after it had already swung past the sun and was heading out. We caught it too late. Borisov gave us months of observation time, but was smaller. 3 I-Atlas was detected while still inbound, 670 million kilometers from Earth, giving astronomers a full approach window to study an active interstellar comet from arrival to departure. The orbital eccentricity tells the story. An eccentricity of 0 is a perfect circle. An eccentricity of 0.999 is a stretched ellipse. An eccentricity above 1 means the object isn't bound to the sun. It came from somewhere else, and it's leaving. 3 I-Atlas has an eccentricity of 6.137. That's not just hyperbolic, that's violently hyperbolic. Oumuamua had 1.2. Borisov had 3.4. 3. I-Atlas is moving faster relative to the sun than any interstellar visitor we've confirmed. When it entered the solar system, it was traveling at 58 kilometers per second. That's the hyperbolic excess velocity, the speed it maintains independent of the sun's gravity. For comparison, Oumuamua entered at 26 kilometers per second, Borisov at 32. 3. I-Atlas is nearly twice as fast as the first interstellar object. At perihelion on October 29th, gravity will accelerate it to 68 kilometers per second, but once it clears the sun's influence, it drops back to that baseline 58 kilometers per second and keeps that speed for millions of years across the galaxy. The trajectory reconstruction places its origin in either the Milky Way's thin disk or thick disk. The thick disk is older, metal-poor, populated by stars 7 to 14 billion years old. A July 2025 study led by Matthew Hopkins estimated with 68% confidence that 3 I-Atlas is between 7.6 and 14 billion years old based on its galactic velocity components. If it came from the thick disk, this comet is older than Earth. older than the Sun. It formed around a star that existed before our solar system condensed from its protoplanetary disk. For potentially billions of years, it drifted through the void between stars, preserving the chemistry of its birth environment in frozen ices. Now it's warming up. Hubble imaged it on July 21st, when it was 277 million miles from Earth. The photograph shows a teardrop-shaped cocoon of dust streaming off the nucleus. Because Hubble tracked the moving comet, the background stars appear as streaks. The nucleus itself remains unresolved, but the size estimates narrow as more data arrives. As of August 20th, Hubble observations constrained the diameter to no less than 440 meters and no greater than 5.6 kilometers. Most likely estimate under 1 kilometer. That's still massive compared to Oumuamua's estimated 200 meters. And unlike Oumuamua, which showed no clear cometary activity, 3. I-Atlas has a coma spanning 26,400 by 24,700 kilometers. As of mid-August, that's twice Earth's diameter. The coma is slightly elliptical, not perfectly round, suggesting asymmetric outgassing from specific vents or cracks on the rotating nucleus. Water ice present, but subordinate. Carbon monoxide detected. Carbonyl sulfide detected. The carbon dioxide to water ratio is abnormal compared to solar system comets. This suggests formation in an extremely cold environment far from a parent star, where carbon dioxide freezes solid before water does. The Very Large Telescope added more data. Cyanide gas confirmed in the coma. Atomic nickel vapor detected in concentrations similar to solar system comets. Nickel in a comet's coma is rare but not unprecedented. The nickel detection came from observations in July and August 2025 using the VLT's spectrometers. This raised questions. Nickel typically requires high temperatures to vaporize. Yet 3. I-Atlas was releasing nickel vapor at enormous distances from the Sun, where temperatures remain frigid. One hypothesis. The nickel is bound in volatile compounds that sublimate at lower temperatures. Another, the comet has been exposed to interstellar radiation for so long that surface chemistry has altered. That's water vapor breaking down into hydroxyl radicals under ultraviolet sunlight, 40 kilograms per second at 3 times the Earth-Sun distance. For context, a fire hydrant at full blast outputs about 60 liters per second, roughly 60 kilograms. This comet was hemorrhaging water like a broken hydrant while still beyond Mars' orbit. And that was in August. By October, as it closed on perihelion, activity ramped up. The James Clerk Maxwell Telescope measured hydrogen cyanide production on September 7th, 1.5 times 10 to the 25th molecules per second. By September 14th, that rate had tripled to 4.5 times 10 to the 25th molecules per second. 2 kilograms per second of hydrogen cyanide streaming into space. The cyanide coma on September 15th measured 180,000 kilometers across, elongated along the antisolar direction. A visible dust tail stretched 100,000 kilometers. The Gemini North Telescope in Hawaii and Gemini South in Chile both imaged the comet multiple times through August and September. Gemini South captured a clear image on August 27th showing the compact coma and dust tail. The colors came from 3 filters: red, green, blue. The tail pointed away from the Sun as expected, but earlier observations in late July and early August showed something unusual: an anti-tail, a narrow jet pointing toward the Sun. This isn't an optical illusion from viewing geometry. Ground-based observations from the 2-meter twin telescope at Tide Observatory in the Canary Islands confirmed the sunward jet on multiple dates. By mid-September, the anti-tail had faded and a more conventional tail emerged. The jet transition suggests non-uniform surface activity on a rotating nucleus, with active regions that turn on and off as they face the Sun. Polarimetric observations. By the Very Large Telescope, Nordic Optical Telescope, and Rosen Observatory in July and August revealed high negative polarization at small phase angles. The light reflected from the coma had its oscillations oriented along the Sun-Comet observer plane more than expected. This polarization signature resembles trans-Neptunian objects and implies the coma contains a mixture of icy and dark material. Dark organic compounds, perhaps. Tholins, the reddish-brown polymers that form when simple carbon compounds are irradiated. If 3 I-Atlas spent millions of years exposed to cosmic rays in interstellar space, its surface could have built up a dark lag deposit that now sublimates as it heats. Closest approach, 18 million miles, 0.19 astronomical units. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express both turned their cameras toward the visitor. CASS, the color and stereo surface imaging system on the Trace Gas Orbiter, captured images using 5-second exposures. The comet was 50,000 times fainter than what the orbiter typically images when photographing the Martian surface. Nevertheless, The coma was visible. Mars Express used its high-resolution stereo camera. The observations happened between October 1st and 7th, covering the comet's closest approach window. Distance prevented resolving the nucleus, but the extended coma and activity level were documented from a vantage point unavailable to Earth-based observers. That's when 3 I-Atlas aligned on the opposite side of the Sun relative to Earth. For any Earth-based telescope, the comet was hidden in the Sun's glare. Solar elongation, the angular separation between the Sun and the comet in our sky, dropped below 30 degrees on October 1st and stayed below that threshold until November 9th. Between October 18th and 24th, the only observations came from the GOES-19 weather satellite, which has a viewing geometry that allows it to see objects near the Sun down to magnitude 12. The comet faded from magnitude 12 to fainter as it closed on perihelion, but GOES maintained limited tracking. Ground observatories went dark. Space telescopes on the daylit side of Earth couldn't point near the Sun without risking instrument damage. And on October 29th at 11:47 UTC, 3 I-Atlas reached perihelion, 1.36 astronomical units from the Sun, 203 million kilometers, 126 million miles, just inside Mars orbit, just outside Earth orbit, and completely unobservable from Earth for 8 days. If the nucleus is structurally weak, thermal stress can crack it apart like Comet Shoemaker-Levy 9 broke apart near Jupiter in 1994, or like 2, I-Borisov showed signs of fragmenting near perihelion in 2019. The moments around perihelion reveal a comet's internal structure and composition better than any other phase of its orbit. And for 3, I-Atlas, that critical window occurred behind the Sun, where Earth's instruments couldn't see. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, was positioned on the far side of the Sun. JUICE is currently en route to Jupiter, but in November 2025, it passes within 64 million kilometers of 3 I-Atlas. That's November 4th, 6 days after perihelion. JUICE's instruments include JANUS, a visible light imager, MAGIS, an infrared spectrometer, and SWI, a sub-millimeter wave instrument. All 3 can observe the comet post-perihelion and measure coma composition, dust properties, and surface characteristics if the nucleus becomes resolved. However, JUICE is using its main high-gain antenna as a heat shield while close to the Sun, forcing it to transmit data via a smaller medium-gain antenna at reduced rates. Data from the 3 I-Atlas observations won't reach Earth until February 2026, 3 months after perihelion. By then, the comet will be accelerating outward, fading as it recedes from the Sun's warmth. Juno's ultraviolet spectrograph, UVS, its infrared auroral mapper, GIRAM, and its microwave radiometer, MWR, can all study the comet's coma and potentially detect surface emissions, but March is nearly 5 months after perihelion. The comet will be cold again by then, activity dropping, coma shrinking. The window of peak observation happened in late October, hidden behind the Sun. We missed it. NASA's Europa Clipper, en route to Jupiter, flew in line with 3 I-Atlas's ion tail between October 30th and November 6th. If the solar wind carried ionized particles from the comet's coma outward fast enough, and if Europa Clipper's instruments were sensitive enough, it might have detected cometary ions streaming past. The ESA's Hera spacecraft, heading to the asteroid Didymos, was also positioned to potentially intercept solar wind packets carrying 3 I-Atlas ions in late October. Both spacecraft encounters depend on solar wind speed, ion production rate, and instrumental sensitivity. Results from these encounters haven't been released as of late October 2025. The comet emerges from behind the Sun, with solar elongation increasing, visibility improving, but brightness fading. Peak magnitude estimates range from 11.5 to 12 before perihelion. Post-perihelion, the comet dims as it races away from the Sun and Earth simultaneously. By December 19th, it passes closest to Earth, 1.8 astronomical units, 269 million kilometers, 167 million miles, closest to Earth, but already cooling down. The comet moves through the constellations Virgo and Leo in December, fainter than magnitude 12, requiring telescopes with apertures of at least 3 to 4.5 inches, using image stacking techniques to detect the faint moving target. The timeline after closest Earth approach: Venus flyby on November 3rd at 0.65 astronomical units, Jupiter flyby on March 16th, 2026 at 0.36 astronomical units, then nothing. 3. I-Atlas exits the solar system, returning to interstellar space, maintaining its 58 kilometers per second velocity relative to the local standard of rest. It will never return. This is humanity's only chance to study this particular visitor. On October 21st, 2025, The same day 3 I-Atlas reached solar conjunction, the Minor Planet Center published Electronic Circular MPEC 2025 U142. The subject? Announcement of IAW and Comet Astrometry Campaign. The International Asteroid Warning Network is a United Nations endorsed planetary defense collaboration of organizations and individual astronomers who detect, monitor, and characterize potentially hazardous asteroids and near-Earth objects. IAWN was formed following UN recommendations and has conducted observing campaigns roughly once per year since 2017 to test global response capabilities. The TC4 campaign in 2017, the KW4 campaign in 2019. The Apophis campaign in 2020 to 2021, the tabletop exercises in 2021 and 2023. Each exercise refined the procedures for detecting, tracking, and assessing impact probabilities for threatening objects. And now, for the first time, IAWN is targeting an interstellar object. Cometary bodies are extended with morphological features, comae and tails, that can systematically pull their centroid measurements off their central brightness peak, presenting challenges to estimate comet trajectories. The International Asteroid Warning Network announces a comet campaign from November 27, 2025 through January 27, 2026 to introduce methods for improving astrometry from comet observations. The campaign will target Comet 3 I-Atlas to exercise the capability of the observing community to extract accurate astrometry. To prepare for the campaign, we will hold a workshop on techniques to correctly measure comet astrometry. Registration is required by November 7th for the workshop, and only those participants that attend the workshop can participate in the campaign. Campaign kickoff, November 25th at 1500 UTC, a 1-hour coordination call. Active observing window, November 27th through January 27th. Data submissions in ADS format, the astrometric data, exchange standard used by the Minor Planet Center. Participants must have an active Minor Planet Center observatory code. This restricts participation to professional observatories and advanced amateur installations that have demonstrated measurement precision. The requirement for mandatory workshop attendance and the restriction to trained observers is standard procedure for IAWN campaigns. The goal is quality control. Astrometric measurements need sub-arc-second precision to refine orbital elements. A single poorly calibrated measurement can skew the entire orbital solution. The center of the Gaussian corresponds to the nucleus position. Simple. But a comet has a coma, a diffuse cloud of gas and dust that extends tens of thousands or hundreds of thousands of kilometers from the nucleus. The coma is brightest near the nucleus, but trails off gradually, often asymmetrically. Jets and tails create elongated structures. The brightest part of the coma, the photometric peak, doesn't necessarily coincide with the nucleus position. Measuring the centroid of the coma can place the comet's position tens or hundreds of kilometers off from the actual nucleus. For orbit predictions, that error cascades. Feed the wrong positions into the orbital element calculations, and the predicted future positions drift. The impact probability estimates shift, the close approach predictions change. Astronomers had to develop specialized measurement techniques, fitting multiple Gaussian components to separate the nucleus from the coma glow. The final orbit was refined enough to predict the Mars flyby distance to within a few thousand kilometers, but early predictions had error bars spanning hundreds of thousands of kilometers. Siding Spring was a solar system comet with years of tracking data. 3. I-Atlas is an interstellar comet with only months of data before it leaves forever. The astrometry needs to be precise. Techniques include multiband photometry to distinguish dust from gas emissions, morphological modeling to map coma structure, and nucleus isolation algorithms that subtract the coma contribution. These methods are computationally intensive and require careful calibration. The workshop on November 10th will walk participants through the procedures. Then the campaign begins, with observers worldwide submitting measurements that get compared, cross-checked, and fed into updated orbital solutions. The goal is to refine 3, I-Atlas's trajectory prediction to the point where the December 19th Earth closest approach distance is known within a few thousand kilometers, and the March 16th Jupiter flyby distance is equally precise. This is the 8th IAWN observing campaign since 2017. Previous campaigns targeted real asteroids with known orbits that were temporarily removed from the monitoring database to simulate new discoveries. The TC4 campaign in October 2017 tracked asteroid 2012 TC4 during its close Earth flyby at 44,000 kilometers distance. Over 70 people from 14 countries participated. Goldstone and Green Bank radars acquired data. Optical telescopes worldwide measured rotation rates and light curves. The exercise confirmed that the global network could detect, track, and rule out impact threats within days. The KW4 campaign in May 2019 focused on the binary asteroid 1999 KW4. The primary body measured 1,300 meters across with a 400-meter moon. Observations tested the ability to characterize binary systems, since roughly 1 in 7 asteroids are binary. Scores of astronomers participated, measuring orbital dynamics and surface properties. The Apophis campaign in December 2020 to March 2021 used the close approach of asteroid 99,942 Apophis, which passed Earth at 17 million kilometers. Over 100 astronomers from 18 countries tracked Apophis, measured its size and spin, and refined its orbit to rule out future impacts for the next century. These campaigns proved the system works for asteroids. Comets are harder. The 2024 planning documents show IAWN had been preparing a fall 2025 comet campaign since the previous year. The intent was to exercise capabilities for measuring the position of comets, which pose additional astrometric challenges as they appear as fuzzy, extended objects compared to point-like asteroids in a telescope's field of view. When 3 IATLAS was discovered in July 2025, IAWN had its target, an active comet with a well-defined observing window post-perihelion, an object of high scientific interest that would naturally attract global observational coverage, and an interstellar visitor, the first interstellar object ever targeted by an IAWN campaign. The campaign tests planetary defense procedures on the most exotic object type. If the network can accurately track an interstellar comet with uncertain composition, variable activity, and hyperbolic velocity, it can track anything. Why require mandatory training for a standard astrometry exercise? Why restrict participation to workshop attendees only? Online speculation suggested the campaign was a cover for undisclosed concerns about the comet's trajectory or nature. Some pointed to the fact that 3 IATLAS would be hidden from Earth during perihelion, the optimal time for any hypothetical trajectory change. Others noted the comet's unusual chemistry, the anti-tail, the high nickel to cyanide ratio, and the alignment of its orbit within 5 degrees of the ecliptic plane, which is statistically unlikely for a randomly arriving interstellar object. Harvard astronomer Avi Loeb, who has advocated for investigating interstellar objects as potential technological artifacts, published a white paper on September 30th, 2025, to the United Nations arguing for coordinated global scientific research to maximize observational coverage of 3 IATLAS. Loeb's argument: if an interstellar object showed signs of propulsion or released probes near perihelion, humanity should be watching. The IAWN announcement followed 3 weeks later. 3. IATLAS is an interstellar comet with unique scientific value. The campaign is a training exercise, the 8th in a series designed to improve global astrometric capabilities. The workshop ensures all participants use consistent measurement techniques, so the data is comparable. The mandatory attendance requirement maintains quality control. The timing coincides with the comet's reappearance in November after solar conjunction, providing a 2-month observing window before the comet fades below practical detection limits in late January 2026. The IAWN website states explicitly, while it poses no threat, Comet 3. IATLAS presents a great opportunity for the IAWN community to perform an observing exercise due to its prolonged observability from Earth and high interest to the scientific community. 3. IATLAS' closest approach to Earth is 1.8 astronomical units in December. It never comes closer than 167 million miles. For comparison, the Moon is 240,000 miles away. 3. IATLAS is 700 times farther. There is zero impact risk. The orbital calculations based on July through September observations have refined the trajectory to high precision. The perihelion date was predicted as October 29th at 11:47 UTC plus or minus 1 minute. The actual perihelion occurred within that window. The December 19th Earth closest approach is predicted to within a few thousand kilometers. The comet's hyperbolic trajectory is locked in. Gravitational perturbations from planets might alter its path by tiny amounts, but the overall trajectory is determined by its enormous velocity and eccentricity. 3. IATLAS will exit the solar system regardless of what happens near perihelion. The Oberth maneuver hypothesis. The idea that a spacecraft could use perihelion, the point of maximum velocity and minimum distance to the Sun, to execute an efficient trajectory change by burning propellant at the moment of peak kinetic energy. This is real astronautics. The Oberth effect is well established. A velocity change applied at perihelion yields more energy gain than the same velocity change applied elsewhere in the orbit. If 3. IATLAS were artificial, a mothership carrying probes, perihelion, would be the optimal time to release those probes on trajectories toward inner system targets. Loeb's September paper calculated the required delta V for mini-probes to slow down from 3, or on Atlas's perihelion velocity of 68 kilometers per second to match Earth's orbital velocity of 30 kilometers per second. The result? Feasible for small probes with compact propulsion systems. The hypothesis is internally consistent but requires 3I Atlas to be artificial, which requires evidence. The evidence cited, the ecliptic alignment within 5 degrees, which has a 0.2% probability for a randomly oriented interstellar object. The anti-tail sunward jet in July and August, which differs from typical cometary outgassing patterns. The nucleus mass estimated at 1,000,000 times Oumuamua's mass and 1,000 times Borisov's mass while moving faster than both, a combination with less than 0.1% probability. The arrival time fine-tuned to bring it close to Mars, Venus, and Jupiter while remaining unobservable from Earth at perihelion with a 0.005% probability. The nickel to cyanide ratio orders of magnitude higher than known comets, including Borisov, with less than 1% probability. Loeb compiled these probabilities and multiplied them, yielding a cumulative likelihood below 1 in 10 quadrillion for 3R. I-Atlas's observed properties to arise naturally. Therefore, he argues, it warrants investigation as a potential technological object. The counterargument: low probability doesn't equal impossibility. 3. I-Atlas is one data point. With only 3 confirmed interstellar objects, the sample size is too small to establish statistical norms. Oumuamua was anomalous, elongated, tumbling, non-gravitational acceleration, no visible coma. Borisov was normal, a typical active comet with standard chemistry. 3. I-Atlas is somewhere in between, active like Borisov, but with unusual chemistry and orbital properties. The diversity suggests interstellar objects come in many types, reflecting the variety of star systems and planetary formation environments across the galaxy. The nickel detection, while rare, has precedent. Iron meteorites contain nickel-iron alloys. Some asteroids have metallic surfaces. If 3I Atlas formed near a star with unusual metallicity, high nickel abundance could be incorporated into volatile compounds that sublimate at low temperatures. The anti-tail could result from dust grain dynamics, where larger grains lag behind the nucleus and reflect sunlight forward. The ecliptic alignment could be coincidence or could reflect the galactic plane's orientation relative to the solar system at the time of 3 Atlas's arrival. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the IAWN official campaign page at iawn.net/obscamp/3. I_Atlas, the official NASA 3. I-Atlas page updated through October 2025, and peer-reviewed literature including the Planetary Science journal study on the Apophis exercise published May 31st, 2022. These are the actual agency documents and scientific papers, not secondary news sources. Now back to the information. Davenport from the SETI Institute noted its galactic trajectory aligns with the thick disk of the Milky Way, suggesting millions or hundreds of millions of years of interstellar drift. Dr. Puzia from Pontifical Catholic University of Chile observed its spectroscopy and called the chemistry an important marker for where this planetary building block came from. Dr. Meach from the University of Hawaii, who led observations with Gemini North, emphasized that 3I Atlas offers an unprecedented glimpse into material from another star system. The European Space Agency's official FAQ on 3 Atlas states, planetary scientists generally see the evidence as consistent with a natural body, an interstellar comet that simply reflects the diversity of environments in the Milky Way. NASA's official statement, Comet 3. I-Atlas is the third known object from outside our solar system to be discovered passing through our celestial neighborhood. Astronomers have categorized this object as interstellar because of the hyperbolic shape of its orbital path. It does not follow a closed orbital path about the Sun. When the orbit of 3I Atlas is traced into the past, the comet clearly originates from outside our solar system. Between November 27th and January 27th, dozens of observatories will measure 3I Atlas's position with sub-arc-second precision. The measurements will refine the orbital elements to within meters per second velocity accuracy and kilometers per day position accuracy. If 3. I-Atlas deviates from its predicted gravitational trajectory by even a small amount, the campaign will detect it. If the comet releases objects, fragments, or exhibits non-gravitational acceleration inconsistent with outgassing, the measurements will reveal it. If the comet behaves exactly as a natural comet should, matching all predictions, the campaign will confirm it. The results will be public. The Minor Planet Center publishes all astrometric data submissions. The updated orbital solutions will appear in electronic circulars. The campaign will conclude with a summary report detailing the astrometric techniques used, the measurement precision achieved, and the lessons learned for future interstellar visitor tracking. The Vera Rubin Observatory, scheduled to begin operations in late 2025, will scan the entire southern sky every few nights for a decade. Projections estimate Rubin will detect dozens to hundreds of interstellar objects during its legacy survey of space and time. Most will be faint, moving fast, and observable for only weeks or months before fading beyond detection limits. The ability to rapidly mobilize global observatories, conduct coordinated measurements, and extract accurate astrometry from extended cometary sources will be critical. The 3 iAtlas campaign is practice. The next interstellar comet could arrive next year, or 5 years from now, or next month. We need to be ready. When asteroid 2012 TC4 approached Earth in October 2017, the exercise wasn't just about tracking the rock. It tested communications between observatories, data flow to the Minor Planet Center, modeling at JPL's Center for Near-Earth Object Studies, hazard assessment by NASA's Planetary Defense Coordination Office, and information sharing with international partners, including ESA and the UN Office for Outer Space Affairs. The exercise revealed bottlenecks in data processing, gaps in communication protocols, and areas where redundancy improved reliability. Each subsequent campaign refined the procedures. The 3 iAtlas campaign adds complexity because the target is interstellar. If a hazardous asteroid is detected, planetary defense planners have years to decades to prepare a deflection mission. If an interstellar object arrives on a threatening trajectory, the warning time is months. The inbound velocity is higher. The deflection requirements are more severe. Testing procedures now, with a benign target, prepares for a scenario where the next interstellar visitor isn't benign. The comet had been captured by Jupiter's gravity, torn apart into fragments, and those fragments plunged into Jupiter's atmosphere over 6 days, creating impact scars larger than Earth. The energy release from the largest impact exceeded 6 million megatons of TNT. That's 100 times the entire global nuclear arsenal. If a similar object hit Earth, it would be an extinction event. Shoemaker Levy 9 was discovered only 16 months before impact. If it had been on an Earth trajectory, there would have been no time to launch a deflection mission. We would have watched it arrive. The asteroid that killed the dinosaurs 66 million years ago was estimated at 10 kilometers diameter. The Chicxulub impact released energy equivalent to 10 billion Hiroshima bombs. The impact winter that followed collapsed the global ecosystem. 3. iAtlas, at its maximum estimated size of 5.6 kilometers, is half that diameter. If it were on an Earth intercept trajectory traveling at 68 kilometers per second, the kinetic energy at impact would be roughly 100 times the dinosaur killer event. Velocity matters. A 10-kilometer asteroid moving at 20 kilometers per second delivers a certain energy. A 5-kilometer comet moving at 70 kilometers per second delivers more energy because kinetic energy scales with the square of velocity. 3. iAtlas isn't on an intercept trajectory. It's not a threat. But the thought exercise is clear. An interstellar object could arrive at any time, moving faster than anything native to our solar system, and if it's aimed at Earth, the warning time is minimal. It's preparation for understanding how to track, characterize, and predict the trajectory of an object that behaves differently than solar system objects. The techniques developed now will apply to the next interstellar visitor, and the next, and the one after that. Rubin Observatory will find them, and Atlas will find them. Pan-STARRS will find them. The discovery rate is about to increase by orders of magnitude. Within a decade, we might have catalogs of hundreds of interstellar objects. Each one is a probe into the chemistry, dynamics, and formation history of other star systems. Each one tests our ability to rapidly assess whether it's a hazard. Each one is a reminder that our solar system is not isolated. We're part of a galactic ecosystem where objects routinely cross between star systems, carrying with them the imprints of their origins. 3. iAtlas reappears in November. Observers will track it through December as it passes closest to Earth. Telescopes will continue monitoring through January as it fades below magnitude 12, then magnitude 13, then 14. By late January, only the largest professional instruments will be able to detect it. By February, it's gone. The JUICE data will arrive in February, 3 months after perihelion, providing the only spacecraft-based observations of the comet near its most active phase. The Juno data will arrive in March or later after the Jupiter encounter. By then, 3. iAtlas will be beyond Jupiter's orbit, accelerating toward the heliopause, the boundary where the sun's influence fades and interstellar space begins. It will cross that boundary in a few decades, moving at 58 kilometers per second relative to the sun. Over the next million years, it will travel 18 light years. Over 10 million years, 180 light years. Over a billion years, it could traverse the galaxy multiple times, potentially entering another star system, warming again, outgassing again, observed by astronomers on another world if they exist, and if they have telescopes. The astrometric campaign will conclude on January 27, 2026. The workshop attendees will have submitted measurements over 2 months, refining the comet's trajectory incrementally with each new data point. The final orbital solution will be published. The close approach distances to Earth, Venus, Jupiter will be confirmed to kilometer-level precision. The exit velocity will be calculated. The interstellar trajectory will be mapped backward to identify possible origin systems, though pinpointing the exact star of origin is nearly impossible given the galactic orbital uncertainties over millions of years. The campaign report will detail the measurement techniques, the precision achieved, the challenges encountered, and the recommendations for future interstellar object tracking. That report will become part of the Planetary Defense Knowledge Base, a document that future astronomers reference when the next interstellar visitor arrives. 167 million miles, 700 times the Moon's distance. It will be in the morning sky, visible to telescopes 8 inches or larger in aperture using image stacking to detect the faint, fuzzy target moving against the star field. Amateur astronomers with the right equipment will photograph it, professional observatories will measure its position, data will flow to the minor planet center, the orbital elements will update. And somewhere in a database, a record will note 3I Atlas, comet, interstellar origin, hyperbolic orbit, perihelion. October 29th, 2025. Closest Earth approach. December 19th, 2025. Permanently exiting solar system, never to return. One line in a catalog. One data point in humanity's growing knowledge of the galaxy. The radar astronomers who attempted detection and failed because the target was too distant. The planetary scientists who modeled the formation environment. The dynamicists who calculated the orbit. The spacecraft teams who repurposed Mars and Jupiter missions to observe an unexpected visitor. The campaign organizers who coordinated global observations, the workshop instructors who taught centroid extraction techniques, the data processors who compiled measurements from dozens of observatories, the modelers who refined the trajectory, the defense planners who used the exercise to test protocols, the journalists who reported the findings, and the public who looked up, knowing that somewhere in the darkness between stars, objects like 3I Atlas drift for eons, occasionally intersecting the gravitational wells of solar systems like ours, offering a brief window to study the cosmos beyond our sun. It's about readiness. When 3I Atlas exits the solar system in 2026, it will leave behind data, Hubble images, Webb spectra, Gemini photographs, Mars orbiter observations, JUICE measurements, Juno flyby data, ground-based astrometry from 50 observatories across 6 continents, light curves showing rotation, polarimetry revealing surface composition, coma models mapping gas production, dust tail analysis tracking particle sizes, nuclear size, estimates constraining mass. And an orbital solution refined to the point where we can predict its position 1,000 years from now within a few thousand kilometers. All of that data compiled, analyzed, peer-reviewed, published, archived, ready for the next time. Ready for the scenario where the interstellar visitor isn't a comet on a safe trajectory. Ready for the call that says, we detected something, it's moving fast, it's incoming, we have 6 months, what do we do? We know how to predict its trajectory. We've tested the network. We've refined the procedures. We've coordinated internationally. We've proven the system works. That's what the 3I Atlas orbit prediction campaign is. Not a response to an imminent threat, not a cover-up, not a warning, a drill. A test, a refinement of capabilities developed over years of incremental improvement, from the first TC4 campaign in 2017 to this, the 8th campaign, targeting the 3rd interstellar object humanity has ever confirmed. And in late January 2026, when the campaign concludes and the final report is written, and 3I Atlas fades beyond detection, the system will be stronger, the procedures will be sharper, the global network will be more coordinated, the astrometric techniques will be more precise. And when the next interstellar object appears, whether it's next month or next decade, we'll be ready to observe it, measure it, track it, and understand it. That's the point. Not panic, not speculation, readiness. The Vera Rubin Observatory began science validation observations in June 2025. It serendipitously imaged 3I Atlas from June 21st to July 3rd, before the official discovery. If Rubin had started observations 2 weeks earlier, it would have discovered the comet before Atlas. That's how close we are to the era of routine interstellar object detection. Within a year, Rubin will be scanning the sky every 3 nights, capturing everything that moves down to magnitude 24. the discovery rate will explode. Dozens of interstellar objects, hundreds over a decade. Each one a new data point, each one a test of our capabilities. Each one a reminder that space is not empty and the solar system is not isolated. We live in a galaxy where matter flows between stars, carrying with it the history of distant worlds. A cold environment rich in carbon dioxide, a region where nickel found its way into volatile compounds. A disk of material that condensed into planetesimals and comets billions of years ago, and one of those comets was ejected, perhaps by a close encounter with a giant planet, perhaps by a passing star, and it drifted for millions of years, tens of millions, hundreds of millions, across light years of void, until July 1st, 2025, when a telescope in Chile caught it entering our solar system. For a few months it warmed, it outgassed, it glowed. Humanity watched, instruments measured, data accumulated. And now it's cooling again, racing outward, returning to the dark. In February 2026, JUICE data will reveal what it looked like near perihelion. In March, Juno data will add details from the Jupiter encounter. But by then, 3I Atlas will be gone, fading into the black, one more drifting remnant of a star system that died before Earth formed. The only trace it leaves behind is knowledge, numbers, measurements, spectra, images, proof that we can track these visitors, proof that we can learn from them. Proof that when the next one arrives, we'll be watching. By January 27th, the exercise concludes. The report is written, the lessons are documented. And the next time an interstellar object appears, the network activates faster, operates smoother, delivers more precise results. That's the goal, that's the outcome. That's why, on October 21st, 2025, while 3I Atlas hid behind the sun at the peak of its activity, the International Asteroid Warning Network published a campaign announcement. Not because 3I Atlas is a threat, because it's an opportunity. An opportunity to test, to train, to refine. An opportunity to turn an exotic visitor into a practical exercise. An opportunity to ensure that when the day comes and the object isn't benign, we're ready. 2 months of observations, dozens of telescopes, hundreds of measurements. One interstellar comet, one refined trajectory, one stronger planetary defense network. That's the story. That's the reality. No hype, just work.